We're going to start combinations now as our next counting method. A combination is a selection of objects without regard to order. It is sort of like a permutation, but order. Now here I have order, position, or ranking doesn't matter. So it's hard to picture initially, but hopefully feel free to ask questions in class to differentiate perms and comps. And I hope to provide you with a few examples. So the notation NCR is often used, and you'll find this in your calculator, NCR. And that is used to represent the number of combinations of R items taken from a set of N distinct items. For the combination formula, if you choose to calculate it more in a manual way, N choose R is equal, by the way, we often call this C choose. N choose R is equal to N factorial divided by N minus R factorial times R factorial. It's very similar to a permutation, but really you just have to divide out the fact that order doesn't matter. So let's just do this first example, and hopefully we're going to differentiate it between perms and comps. Very similar. So let us consider the letters P, Q, and R. How many ways can these letters be permutated? So here it is. This is our permutation. We know how to do this. Well, here's our first letter. Here's our second letter. Here's our third letter. So we have three choices, three different letters can go in that one, two different letters can go in the second one, and one letter. So there's 6 ways that it can be permutated. So when we permutate PQR is distinct from QPR, which is different from RPQ, and etc., etc. So order really does matter. Now, how many ways can this be combined? Well, there's three objects, 1, 2, 3, and we're going to choose 3 at a time, so it's 3 choose 3. And this is just 1. So basically, I have these 3 letters. How many ways can they be combined? And what I mean by that is we are not going to distinguish between P, Q, and R, or R, P, and Q. That is, those are going to be the same. Now, it may not make sense with letters, but if you think of it in people, if there are 4 people sitting at the table, how many different ways can we combine these to form groups of 3? Well, provided that there's no positions such as president, vice president, or secretary, a group of 3 can be Amy, Bill, and Paul. But somebody else says, whoa, wait a second, Paul, Amy, and Bill. You would say, well, those 2 are the same group. So the way that we order the people in the group doesn't matter. So this would be a combination. Now, there are 10 members of a student council. How many ways can 4 of the members be chosen to serve on the dance committee? So we have a total number of 10 objects, and we're just going to choose 4 of them. So this would be 10, choose 4. It's in the probability menu of your calculator, and I'm just going to find out 10, choose 4, and that is 210. Now, permutation and combination, well, if you have, what is the difference between the 2? I'm just going to say Amy, Bill, Clayton, and Diane. Now I'm going to A, B, C, D. All these are going to define, and there might be one president, and there might be one vice president, and there might be one secretary and treasurer for the dance committee, say. But we would say it might be a different committee if it was Bill, Amy, or Bill who was president, Amy that was vice president, Charlie and Diana. Whereas a combination would be, well, who's on the committee? And people would be, well, order really doesn't matter. There's no order, there's no position or ranking. It's just Amy, Bill, Charlie, and Diane. So a restaurant serves 10 flavors of ice cream. Emily has ordered a large sundae with 3 scoops of ice cream. How many different ice cream combination does Emily have to choose from if she wants each scoop to be a different flavor? Well, we have 10 to choose from. So we have 10 elements, and we're going to choose 3. So this would just simply be 10, choose 3. And all fair and good. And what I get is 10 choose 3 is 120. So there's 100 different combinations that we have. So since we're on the flavor of, or talking about ice cream, let's talk about a combination. And by the way, this is a plate of ice cream. And I'm going to have maybe flavors of banana, lime, and blueberry. Now that would be a combination because if a plate of ice cream is called a sundae and there's 3 different flavors on it, we could say that now just simply moving the position of banana, blueberry, and lemon does not change the nature of the sundae. That is, one person could look at that sundae and see another plate with those 3 flavors and would not think them to be different. However, now let's build an ice cream cone. So with my ice cream cone, let's suppose I put lemon on the bottom. Lime on the bottom, and then I'm going to put banana, and then I'm going to put blueberry. Here, I might suggest that order matters, because if somebody builds another ice cream cone, what they might do is they actually might put blueberry on the bottom, banana in the middle, and lime on the top. To me, those are 2 separate and different ice cream experiences, if you would. So that's the difference between combination and a permutation. Order, position, or ranking do not matter in a combination, but in a permutation, definitely it does.